Our next lecture is going to be the Nicolet lecture, and the awardee is Dr. Karel Schrijver. Dr. Marc DeRosa will be presenting the talk entitled Karel Schrijver, 1958 to 2024, a retrospective. Thank you.
Okay, thanks, Nick. If you know Karel's publication record, you'll know that it's impossible to provide a scientific retrospective in 15 minutes. But I'm going to, as a result, I'm going to pick a few things that I know that Karel was very, very interested in over his career and talk about those. But inevitably, I'm going to skip over large swathes of his scientific research. So I apologize, and especially since I probably biased it toward things that I'm also interested in. But anyway, yeah, as mentioned, Karel unfortunately passed away at the beginning of September. But he did know that he was being awarded this medal, but it came very close to the date on which he died. But I think it's of great consolation to me that he did actually know that he was being awarded this medal, and I think he would have really liked to I mean, in general, he liked giving talks and communicating science, and so this is another such opportunity that he would have liked. So there is a kind of a running theme through all of, or most of Karel's research, I would say. Much of it is very interdisciplinary, and it's specifically interdisciplinary science associated with photospheric magnetic fields, the chromosphere, and the overlying coronae above those photospheric fields on both the sun and other cool stars. And I'll point out in passing here that a useful resource on reading through Karel's scientific career is his memoir that he wrote in the Solar Physics Journal that was published last year. It's a nice, friendly, and somewhat breezy trip through his life experience. It's easy to read on, say, a train ride from Coimbra to Lisbon, for example. It won't take particularly long, but in any case, his very first published paper was this one from 1983, from which this figure is taken. And it shows the correlation between, from a sample of cool stars, it shows the correlation between X-ray fluxes, these are disk-integrated X-ray fluxes, and calcium-2 flux. That's actually the figure on the right. So there's a bunch of cool stars, and the sun is indicated by the line that's sort of in the bottom middle of the diagram. And you know, of course, we observe the sun fairly well over time, and the line just indicates solar minimum and solar maximum, and those are the extent caused by changing solar activity. But what Karel discovered in this paper was that actually, if you subtracted off a baseline level of calcium emission, then you would end up with the figure on the right. And by subtracting off a baseline amount of calcium emission, you're basically sort of normalizing the star to its kind of activity minimum level, more or less, or its basal level. And the excess would be, any excess would just be due to whatever magnetic field is on the disk. And Karel found that there was a very good correlation with that. Versus the X-ray flux, which is also related to how much magnetism is on the disk. And so that sort of propelled him forward in these studies of the relationship between magnetic fields and the emission caused by the overlying corona. And that line of thinking led to a series of papers in the 1980s. There's actually quite a few papers, if you go back into ADS and look, that started with this paper while he was based in Utrecht and concluded with the paper in 1988, I think. It was the last paper in the series, while he was based in Boulder. And so he went to Boulder as a postdoc to join Jeff Linsky's Cool Stars group there. And he really found that environment stimulating because there was lots of Cool Stars research going on in Boulder and in general at that time. So continuing on this theme of calcium observations, in the mid-1990s, Karl joined the Lockheed Martin group headed by Alan Teitel. And there, one of his first projects was to analyze a multi-day time series of calcium filtrograms of the sun. Basically, this was an uninterrupted multi-day time series that was taken during one of the austral summer intervals. And I don't remember exactly how long it was, but I think it's a couple of days or 3 days or something like that. But you have to remember, how hard it is to get uninterrupted observations of solar magnetism. And so these were, and of course this predates SOHO, which I'll get to in a moment. And so he spent a lot of time analyzing, he's sort of the perfect person to do it because he was already thinking a lot about about the interaction between calcium and magnetism. And as Theo just said, this is something that has been well observed, and we make use of these old calcium data for projects like his, solar irradiance related projects. But analyzing this, so this was a time series with, I don't remember exactly what the temporal sampling is, but I think it's on the order of something like tens of minutes or maybe even a little bit less. But in any case, it was mostly uninterrupted, and it started Karl thinking about how magnetism, in particular small-scale photospheric magnetism, evolved on the sun. And that led him throughout the rest of the 90s to really try and figure out dispersal rates or diffusion rates of small-scale flux. It was observed that small-scale flux merged and split fairly often. That also raised the question of how long do these small-scale flux concentrations last? Do they have a tilt angle? And so on and so forth. And this, of course, was greatly helped by the launch of SOHO, and in particular, the MDI instrument on SOHO. And MDI provided magnetograms from space, and this enabled more detailed studies of these types of flux evolution. And I've shown on the right here an image of the type of data that MDI made. MDI was, I think, originally primarily thought to be mostly a helioseismology instrument, and the main data product would be the Dopplograms. And you can see the LNU diagram in the bottom, the spectrum of solar oscillations there on the bottom. And I'm not actually sure to what degree people knew before SOHO was launched how valuable the time series of magnetograms would be from MDI. But now, we've been living with magnetograms from space since the launch of SOHO, which is now, it turns out, almost 30 years ago. And, these are really quite valuable. SOHO took a full disk magnetogram kind of every hour and a half, and as a result, there are only 15 of them every day. So think about that. But in any case, this really helped Karl study small-scale magnetism in a lot of detail. So this image is from what I think is a really unique paper. Karl was always a little clever with naming things, so he called this magnetochemistry, which is basically the study of how individual localized flux elements interacted with each other. And in this paper from 1997, he developed a fairly he developed a statistical model of flux emergence, fragmentation, collision, cancellation in response to the associated observed convection. And this is a model that worked extremely well, and he made sure that, he managed to get this model to mostly agree with observed distributions of flux concentrations on the sun. And, so kind of what you're seeing here, the darkest and the lightest spots are flux concentrations that were identified from MDI. And the lattice structure is an associated supergranular, the boundaries of the supergranular network, essentially, in quiet sun. And so he and a number of other people at Lockheed in particular really spent a lot of time looking at these types of things. And there were these movies made of the flow field, and if you dropped in passive particles that floated in the flow field. You could sort of represent the observed concentrations of flux in the supergranular network. At about the same time, a little bit after SOHO was launched, TRACE was launched. TRACE is was a NASA small explorer that had an EUV imager on it that observed the sun in several narrow bands, including 171, 195, and 284 angstroms that are from various ionization states of iron. And so at the time on SOHO, there was the EIT instrument, which was a full disk EUV imaging instrument, but didn't have the same spatial resolution as TRACE did. TRACE's pixels actually were about the same size as AIA's, but because of various instrumental effects, the actual effective spatial resolution is a little bit worse. But probably more importantly, the exposure time of TRACE was of the order of tens of seconds. And so that really smeared out any of the evolution that we now know happens in the corona. But anyway, TRACE was, a way of trying to link the observed photospheric magnetic flux with the observed, EUV and X-ray fluxes, and this happened. This happened as a result of TRACE. Karel was the science lead for TRACE, and there was a sort of a 50-page paper, which I think was also published in Solar Physics, that was just on a list of various early results from TRACE. This is evidence of how good Karel was at sort of like getting people to like work together. If you've ever been involved with one of these larger projects where you're all trying to like get a paper published, there's lots of emails, lots of time spent getting in touch with people and tracking things down and getting figures and all that. So in parallel with all of this, Karel was expanding the magnetochemistry model to see if he could create a global evolving photospheric flux model that was based on his observations of small-scale flux evolution. This was meant to be a kit that you could apply to other cool stars as well. And so in the figure shown here, he has this A parameter in the model, which is meant to approximate the amount of activity on the disk of the star. And, the sun sort of went from like 1 to 10 on this A parameter, but he also did simulations for a very active star with with an A of 100, which is what's shown on the bottom here, just to see what it would look like, assuming that all other things on what we know from the sun applies to this hypothetical more active star, which is maybe not quite right. Probably the increased magnetism would do things like quench the ability of the convection to move things around. But still, it's useful to get a picture of what other stars might look like. And if you run this model kind of long enough, you'll see that you get these pretty strong star spots building up at the poles at activity minima intervals, which may or may not, probably not, but are sort of like intriguingly representative of, we know that there are large, like other stars have large patches of magnetic fields on them. And Karel was able to sort of get this to sort of automatically happen without changing the solar rubric very much. And then soon thereafter, Karel then realized he could both take actual MDI magnetograms and stick them into the model, and get a representation of the full photospheric solar magnetic field. And because this model was evolving in time, he also thought it'd be useful to try and make forecasts of what the solar photospheric flux would look like a few weeks into the future. And that led to this model, which I'm showing here, which is basically a Carrington map of the flux, which is the very background grayscale image. And then there's a bunch of other stuff on it, which include things like the projection of the heliospheric current sheet from some sort of coronal model. Well, it's the potential field source surface coronal model. That's the dashed black and white line. And also the outlines of open flux regions and things like that. And this work was occurring. I mean, there were some other groups trying to do similar things, like Wang and Sheely and Ward and Harvey. And so there's a lot of, the amount of data that came in through MDI really sort of spurred on all of these activities. And of course, these are, especially the open flux regions are sort of the solar origins of space weather, which is what this whole conference series is about. So putting things together, Karel had a model of how the photospheric flux actually evolves now, and he also wanted to understand how the extrapolated coronal field matched the coronal loops from trace. And this is where I joined the Lockheed group, and he sort of came into my office one day and said, "You have experience with spheres," because I had done these global spherical models of solar convection for my PhD. And he's like, "I need to trace some field lines through a potential field model and put them on the trace images." And I said, "Great. Well, how many images are we talking about here?" He's like, "Well, all of them." And so I'm like, "Oh, well, I guess we need to create some sort of database." And this is kind of how the potential field, the set of downloadable potential field models actually started. So, and I'll note in passing, since this is a space weather conference, that the Schrijver and DeRosa 2003 paper, one of the trace overlays, which is the one on the bottom here, actually contain an example of open field lines where the foot points of the open field lines are actually located within an active region, at least according to the potential field model. And now we think about how much focus the origin of the slow solar wind gets, especially as it relates to space weather applications. And even in 20 years ago, 21 years ago now, we were sort of finding that this could happen. And it sort of just happened naturally as a result of applying idealized models, applying idealized physics to the data that we had at the time. In that paper, there's also the result that during activity maximum, maybe even as high as 50% of the flux open to the heliosphere originates in locations with reasonably high flux densities. And this is mainly because, like, if you have a high region of flux density, and there's open field in it, it will like balloon out and represent a fairly large volume of area of open flux. So I'm going to try and hurry up because I feel like the time is running out. So at this point, the Living with a Star era begins. So Living with a Star is a NASA program that presented the opportunity for interdisciplinary research between the sun and cool stars. This was right up Karel's alley. He was involved with shaping the direction of these types of programs, because at the time he was on the National Academy's Space Studies Board. And the SDO, the Solar Dynamics Observatory, was the first Living with the Stars flagship mission. And HMI and AIA on SDO, of course, were follow-ons to earlier instrumentation, especially MDI and EIT and TRACE. And Karel was the original science lead for AIA, as he had been for TRACE many years earlier. A few other things that Karel was involved with. He was one of the original deans of the Heliophysics Summer School. This is another NASA-sponsored program. I think it was mentioned in the Nicolet medal citation that was read yesterday. But Karel and George Sisko both took on the challenge of implementing the summer school in the mid-2000s, when it was realized that heliophysics is an interdisciplinary science, and that we really need to train researchers of the future in heliophysics if we ever want to advance the field. They discovered fairly quickly that no textbooks were available, and so what did they decide to do? They decided to write their own. And as a result of that, 5 textbooks have come out of these heliophysics summer schools. The first 3 are edited by Karel and George, and the bottom 2 are edited by Karel and Fran Bagenal and Jan Soika. But you can go onto the web page here for the summer school and try some of the problems yourself if you're trying to remember how to do these things. It's an extremely valuable resource for not just early career scientists in heliophysics, but basically anyone. And then probably one of the last things he did before he retired, or at least one of the last things that took up a lot of his time before he retired, was to put together the COSPAR roadmap. the Space Weather Roadmap, which was also mentioned in the citation yesterday. There is, the executive summary, there's a fold-out, two-page fold-out. This is just half of the summary. This is just one of the 2 pages, I should say. But it contained like a list of recommendations, which are all listed over the image of the sun and the coronagraph image there. And so you can see how comprehensive it is. And if you really want to read the full report, you can go to the Advances in Space Research article. And he'll be the first to admit that like putting this together took a lot of time because, as I mentioned earlier, there was all these people involved, and you can look at the disparate sources of knowledge from all these people listed here. So anyway, I think I will end there. I'm probably over time, but I tried to give you a feel for the science that Karel was involved with, as well as his ability to collaborate with lots of people. And it's a shame that he could not be with us here today. Thank you.